believe it when it's said the things I say aren't true. When I knock on the door with 10 roses out the blue, then you've a right to be confused. Fingers crunch beneath my feet, tied a thread to the old door handle standing shut, and you lost your baby teeth.
So, vector line integrals. Vector line integrals. Yay. So we can actually, like the scalar line integrals that we learned, those are useful and they have various applications. However, vector line integrals, there's a lot more that we do in this class anyways, working with vector line integrals. So just an overall view of them, the key difference from scalar line integrals are that these depend on the direction you travel on the curve. Okay, you travel on the curve. So basically, I don't think I explicitly mentioned it, but with scalar line integrals, so scalar, I'm just going to abbreviate, line integrals, with those, direction doesn't matter. So direction does not matter. It's just going to be the same any way you go, whether you go to the left or to the right or whatever, doesn't matter. Okay? And technically, well, I'll explain this on the next slide so I have some room to make a diagram and everything. But so the line integral of a vector field, so line integral of a vector field, and I'll just write F here, vector field F is technically the scalar line integral. So at this point it's like, okay, you just said that they're not the same because there's a key difference, but so this is the scalar line integral, and this is the crucial part here, of the tangential component of F. Okay, so this second part here is very, very important. Tangential component of F, because that basically tells you everything that you're doing, everything that you are doing when you take a vector line integral. Okay, so basically what we have, here's our diagram. So we have like some curve going along, right? All of my curves look the same, I'm sorry, but we'll see. Anyway, so here's a curve, and then here's an example of like a vector field. It doesn't do anything. It doesn't depend on the curve. Okay, they exist independently, basically. So a vector field, it could just do whatever it wants, right? Depending on the function that it wants to do. So it's just like going different directions, stuff like that. So anyways, what we're gonna do is I want to look at a little part of a curve here. So let's say we're looking at this little part. We're gonna zoom in, and the vector integral at this point, the vector at this point determined by F looks like that. Okay, actually I think I'll draw it a little bit bigger. Okay, so let's say it looks like that. So this is our vector at this point as determined by the vector field. So what the second part here means of the tangential component of F. So basically here's our C of t, right? This is our C of t. That's our parameterized curve going along here. And basically at this point, at every point, there's a tangent line, right? So at this point, the tangent line looks something like that, right? And what C prime of t tells you, so this is C prime of t, that'll tell you the slope of the tangent line, okay? So this is the slope of the tangent line there. So basically what we want to find is the tangential component of F. So that kind of should ring a bell. Well, it probably wouldn't ring a bell for me if I was taking the class at this time. But anyways, so it may ring a bell. Tangential component of F is basically saying, here, I'll rewrite that. It's the projection of F onto the tangent line, at P, line at P, and I'll just name that point P. So just at this point, that's all we're studying right now. So basically, projection is found by f dot whatever, right? And then also what is, so this is technically f dot t, where I'll just name this little vector here. T is the line, the vector that goes along the tangent line. But anyway, so this is like our f parallel, if you remember from like whenever you took 32A. But okay, so basically, I'll continue on the next slide. So we have f dot t. But what does that mean, really? So we know what f is, right? That was the vector that was going in kind of independently. That was a vector like that, right? So this is our f, and our t, that's what we have to find, right? So this is like t, okay? But what we're actually interested in is this t hat, okay? So, I mean, these are kind of interchangeable. People just write them like either the normal arrow or the hat, whatever. But what it signifies is the unit tangent vector. Unit tangent vector. So that means that it's a vector that goes in the direction of the tangent line. So first of all, it's parallel to tangent line. And second of all, because it's a unit, it's magnitude. So magnitude equals 1. Magnitude is 1. So that's always useful because 1 is pretty versatile. So basically, to figure out t, so this is the problem now. So what is t? What is this t? Okay. So let's go back to looking at the curve. All right. So we have this curve here, and that is parameterized by c of t. Okay. We've done that before. And then at this point here, so c of t gives you the points on the curve. But c prime of t, if you think about it, so c prime of t gives us slope of tangent line at any point. Right? Okay. So c prime of t will look something like this. It'll actually go along this tangent line here at that point. So this is c prime of t, but the thing is that c prime of t itself, that isn't necessarily a length of 1, okay? So what we have to do now is what's called normalizing. So that just means find the magnitude. So what we have, well, normalize doesn't mean that, sorry. Normalize just means make some vector into a unit vector. Okay, so in order to normalize this, what we do is we take the c prime of t, and we're going to just divide by its magnitude. Okay, that's how you normalize any kind of vector that isn't already of length 1. Alright, so this is our t arrow, or you could put t hat, because it's the unit tangent vector technically. So you could put either one. So let's keep this in mind, and we'll return to our formula. Okay. All right. So what we have is we want f dot t, and then times ds. This is our differential length of the curve. And what this is, this turns into our f depends on c of t. It depends on the point that we're at, which is now parameterized by the curve. So f turns into that. So we have f of c of t, okay? And then we have times t, which we found in the last slide, is now c prime of t divided by its magnitude. So magnitude of c prime of t, okay? And then our ds, remember that was, ds is the same thing as this thing, which was the same as c prime of t, magnitude of that, times dt. So we're going to plug that in for ds, all right? So we have magnitude of c prime of t times dt. So as you can see here, the magnitude values cancel. So we're left with f of c of t dot c prime of t, and then everything times dt, of course. Okay, So when we plug this into our vector line integral, this is what it's going to look like. They'll tell you, evaluate this. Or sometimes they actually write it like this, I believe, in the book. Something like that. But I think that this way is more, it gives you a visual of like what you're doing in your line integral, which is taking the tangential component of f. Okay? So I frequently write it like this. But anyways, so what this is equal to is the following. So this is equal to, from a to b, and again, the a to b is the bounds on t for your curve. So everything depends on a and b, basically. And then f, we're just going to plug this in. So we have f of c of t dotted with c prime of t, and then our dt. Okay? So another way to write this also, so this is like the main thing about vector line integrals. So keep that in mind. This is for vector. So vector line integrals, right? The other one was scalar. So that's that. And then I'll expand a little bit on the next slide. So we have this formula here for the vector line integral. We have f of c of t dotted with c prime of t dt. So this is, in effect, if we break it down into components, right, because then we have our f, oh, sorry, the little dash isn't supposed to be there. F is an F1, an F2, and some F3. Okay? Whoa! I have random brackets being thrown in. Sorry. And then C of t, we said, is equal to some x of t, some y of t, and some z of t. Alright? So we know these. And then, so if we want to write this in a little bit different form, this is what it's going to look like. It is from A to B. And then, let's say we have F1 of, and we're still plugging in C of t, right? So F1 of C of t, F2 of C of t, F3 of C of t, of course, because you plug it into each component, right? That's all I'm doing. I'm just breaking F down into its components. And then the C prime of t now is going to be, to get C prime of t, you take the derivative with respect to t of each component. So that would be dx dt, dy dt, and dz dt. And then at the end we still have our dt sitting there. Alright? So what we can do is when we dot this out, that sounds funny, when you dot this out, is you multiply the first components. So we're going to multiply those together. So times dx dt, I'll just write a little parenthesis here. And then you add it to the product of the second components, which is the following, dy dt, and lastly the third component, the product of the third components, like such. Okay, and then we have our dt sitting out here. So then technically what we can do is cancel the dt up here with all of them on the bottom, right, from each term. So finally, what we get is something that looks like this. So we have from the integral from a to b of some f1 of c of t times dx plus some f2 of c of t times some dy plus f3 of c of t times some dz. Okay, so the point of me doing this whole slide here was just to show you another form of a line integral that you might see. Another form you might see. So that you're not confused and completely like lost when you look at it. Because I know I was the first time I saw this. Some question put in this form, I was like, I don't know what I'm doing. So anyways, just to give you guys a heads up. Alright, so now let's start an example of a vector line integral.